Good morning, good afternoon, and good evening, everyone. My name is Shiyang. I'm a currently assistant professor in Department of Electronical and System Engineering at University of Birmingham. So today I would like to thank, I really appreciate Dr. Liu for providing me the opportunity to present our recent works on liquid metal enabled soft electromechanical actuators. So in today's talk, firstly, I'll give a brief introduction to liquid metals, just in case some of you may never heard about this kind of materials before. Then I'll briefly talk about our recent works on liquid metal electromechanical systems. I'll be covering the actuation mechanism of liquid metal droplets. I'll be talking about liquid metal driven robotic system, as well as using liquid metal droplets themselves as robots. So whenever people mention about liquid metals, I believe most of you have heard similar idea from the movie called Terminator. I myself is a big fan of the sci-fi movies, so I watched this movie since I was a kid. I was fascinated about the idea. Since then, I was very lucky to have opportunity to do further investigation on this kind of fascinating, interesting material. So in reality, I think the most famous liquid metal, or most of you have seen it before, in the very old thermometer is mercury. It has a melting point of around -40 degrees Celsius. And another most commonly used liquid metal is called sodium potassium alloy. And I think it's widely used in nuclear power plant. It has a melting point of -12 degrees approximately. But it's, because sodium potassium is highly reactive, so it's reactive with water, with air, so it's very unsafe to use, especially in a laboratory. Another two metal which have like melting point close to room temperature are cesium and gallium. They have melting point approximately around 29 degrees Celsius, but cesium is also extremely reactive. And the material we're currently working with is called gallium-based liquid metal alloys. And two most famous or widely used this kind of alloys called first is called gallium, which is a alloy of gallium, indium, tin. And secondly is just utility gallium, indium alloy. So this type of liquid metal looks very similar to mercury, has silvery metallic color, but also forms an oxide layer, which I'll be talking about later. I made this table to briefly compare some physical property between mercury, DI water, and one of the liquid metal we use is called gallium. As you can see, the density of gallium is half of that of mercury, but it's still like 6.5 times of water. They all share very similar viscosity, but gallium has much higher substitution than that of water, which is approximately 10 times. As a metal, it has high thermal and electrical conductivities. It has a melting point around 11 degrees, which is below room temperature, so it's liquid at room temperature. But it's not going to freeze until you cool it down to around -19 degrees because of the supercooling effect. Also, it has almost negligible vapor pressure compared to mercury, making it much safer to use in a laboratory or in our daily life. And like gallium, indium, tin are not as toxic as mercury. So I use this figure to summarize some recent advances of the property and application of gallium-based liquid metal alloys. In brief, numerous unique properties of this kind of materials can be harnessed, such as immiscibility to many other solvents. It has surface reactivity, it forms a native oxide layer on the surface. It's fluid, it has high substitution. It can be used as solvent to many other metals. It has catalytic effect, and it has superfluid effect, of course, as the metal has high electrical and thermal conductivity. All these properties can be harnessed and applied through, I call it, 3 embodiments, including bulk, particle, and composites. And numerous applications have been recently developed, including, like, for example, 3D printing, biomedical application, microfluidics, like electrochemistry, energy. So many applications being explored in the past decades. But most of these applications are actually based on the interface or surface of liquid metal. So here I want to quote a very famous phrase from Wolfgang Pauli. He said, "God made the bowl, and the surface was invented by the devil." So in this paper, I call it liquid metal as the devil's elixir, because most of the application actually is enabled by the interface. At the interface, if it's in air, it actually forms a native oxide, which is approximately 3 to 5 nanometers. And this oxide is able to mechanically hold the structure of the freestanding printed droplets. But if you apply a strong acid or base, you are able to remove the oxide, so the liquid metal is going to beat up. And let the substantiation to dominate, so it's going to behave more like mercury. And also on the surface of oxide layer or on the liquid metal, we can coat like macromolecules, including polymers or numerous other molecules to bestow it with additional biofunctionalities. And also the surface oxide allows the liquid metal to wet so many variety of substrates like silicon, glass, gold. So direct printing of liquid metal is possible because of the gallium oxide. So in terms of liquid metal electromechanical systems, 2 categories of properties can be harnessed. Like, first, of course, is fluidic, second is metallic. These properties can be harnessed to generate numerous effects, including, for example, electrochemical oxidation, continuous electrowetting, which I'll be talking about later. And you can also introduce electrocapillarity, electrowetting, electrophoresis, and you can also induce Lorentz force inside liquid metal. All these effects allows us to generate gallium liquid metal based soft electromechanical actuators, and these actuators can be applied into a more complex systems to find their applications in robotics, microfluidics, and electronics. So next, I'll be talking about some actuation mechanisms of liquid metal droplets that can be harnessed to make more complex systems. In this case, I think the most widely used actuating mechanism in the past, like in most of my research, is called continuous electrowetting. To demonstrate this kind of, give an intuitive understanding to show how what continuous electrowetting does to droplets. In this case, I put a droplet of gallium nitride inside a channel which is filled with a solution. The solution can be like, for example, can be a sodium hydroxide solution, can be a sodium chloride solution. And I apply a potential gradient across the channel. The channel is approximately 10 centimeters long and 4 millimeters wide. And the potential gradient, the potential applied is approximately 10 volts. So when I apply the potential gradient, I found that the droplet is able to migrate towards the anode at a very high speed, approximately 10 centimeters per second, because I'm using this is high speed footage. So the actual speed is relatively high. It's approximately 10 centimeters per second. So why this is happening? This is not because of electric forces, because the electric field is super low. If you just divide the 10 volts by like 10 centimeters. So the actuation is actually caused by the electrowetting or alternatively Marconi effect. To briefly introduce why this is happening, here I make a few animation schematics. When you place a droplet liquid metal inside solution, the electrical double layer will form at the interface. Because of the electrical double layer, there will be a voltage drop across this layer, and the voltage drop is approximately 1.5 volts. The higher the solution will have a higher potential. And when you apply external potential gradient, what actually does is it's going to induce imbalance of the voltage drop across this electrical double layer. Because the liquid metal itself is highly conductive, it will remain as equal potential, while the external potential will, like a gradient will form in the solution. So because of the right-hand side, we'll have a high voltage drop across the EDL, while the left-hand side has a less voltage drop based on the Liebman equation, which the surface tension is equal to the maximum surface tension without any electrical double layer minus the energy stored inside the capacitor formed because of the electrical double layer. So the larger voltage drop means that it will give a lower interfacial tension. So in this case, the interfacial tension on the left-hand side is going to be higher than the interfacial tension on the right-hand side. So by applying an external potential gradient, I'm generating a gradient of interfacial tension along the surface. And the consequence of the gradient of interfacial tension is called Marconi effect. It's gonna pull the liquid from the low surface tension area towards the high surface tension area. So in this case, the surface of the droplet will act like conveyor belt, which was going to drive the droplet itself towards the anode. So you can imagine. Here I coat the surface of the liquid metal with some metal particles to show the formation of the Marconi flow upon the application of external potential. Here you can see that the particle on the surface can be stripped off, so the droplet will become like bolded. You can imagine this as you're trying to paddle a boat on a river. The paddle behaves like the surface of liquid metal, which generates the flow. So in this case, the flow will drive the boat move forward. But imagine if you block the droplets, instead of like driving the droplet moving forward, it's gonna pump the liquid, so the liquid backwards. So in this case, imagine that if your boat is blocked by something, the paddle, which is an analogy of Marconi flow, instead of pushing the boat forwards, it's gonna pump the flow backwards. So using this principle, we created a very simple, simple pump called liquid metal enabled pump. Upon the application potential gradient, able to pump liquid inside a closed loop channel. These two principles are fundamental to many of the actuators we developed later on. And another principle we harnessed is actually discovered by Professor Michael Dick's group at NCSU. Their group found that if you oxidize a droplet of liquid metal, you're actually killing the surface tension because you form an oxide layer on the surface. The oxide layer acts like surfactant in like oil, in a water oil based system. So in this case, the oxide layer kills the surface tension and make the liquid metal to expand because of this. The surface tension is near zero, so in theoretically you have infinite surface area. So that's the reason why these branches forms. You can also reduce the surface by applying a reduction potential to restore its surface tension, and then it's gonna beat up to restore to its original spherical droplet. So this is the second mechanism we'll be harnessing to form some of our actuators. So after talking about some fundamental mechanisms for actuating liquid metals, next I'll be talking about some liquid metal droplet-driven robotic systems we developed in the past few years. The first thing came to our mind was just, okay, why not harnessing the droplet, actuation of the droplet itself to use the droplet itself as actuator. So to do this, we directly apply the droplet into a conventional robotic systems. And in the robotic system, we have motor control unit, we have accelerometers. We use electrode control arrays of liquid metal droplets. We call it liquid metal wheels. So we hope to like use conventional control system to see whether it's possible to control the actuation of droplet or use liquid metal droplets to act as like to replace conventional DC motors. And here I hope the video plays. Yes, we show that this is top view. We show that we're able to just simply apply PID control. We can control the movement of a robot and making the follow even like a little bit more complex trajectories. So if we use the pumping idea, we instead of like making kind of like a actuator and motor, we can use liquid metal droplets as propellers to power or to drive a robotic boat. In this case, we have like 16 liquid metal droplets, which are controlled again by the motor control unit, accelerometers, and a lithium-ion battery to make everything untethered. So to do this, let me show if, yes, we are able to propel robotic boats to follow the pre-designed trajectories. So yeah, instead of using conventional mechanical propellers, we can simply use Marconi flow induced by droplets of liquid metal to propel robotic boats, and they're all highly controllable. But those robotic systems have one big drawback. They can only be actuated in the solution, like a salt solution, seawater. So what if we want to do something outside liquid environment? What shall we do? So we came up with the idea of introducing a wheel robot. In this case, we're trying to we just put a big droplets of liquid metal inside a wheel robot, and hopefully by changing the center of gravity of the system, we're able to drive the robot moving forwards and backwards. Here, I'll just quickly show you the footage. Yeah, when we actuate the droplets, we are actually altering the center of gravity, so we're able to drive the wheel robot moving forwards or backwards. Yes, and to make our system even more complex, this is what we tried. We tried the concept called Rotary Motor, which would borrow a concept from the conventional DC motor, but instead of using like electromagnets to drive the rotor, we use liquid metal droplets in this case. So we have 8 units of this kind of liquid metal actuator and to form the rotor. And also we created a liquid metal brush to allow the rotor to rotate, and meanwhile allows the current passing through the rotor and stator to drive each unit of each actuation unit. And because of the liquid interface, the friction is much lower than that of conventional brush, solid contact brush in the DC motor. And such a motor can be integrated or embedded to many other systems to drive vehicles, to drive boats, or many other systems. And so here, the footage shows that the actuation of a untethered vehicle using the liquid metal motor. Yeah, and also you can embed the motor inside the wheel, inside a boat or paddle to drive the paddle wheel. And using the oxidation and reduction mechanism, we next created liquid metal enabled artificial muscle. So basically, we have a liquid metal bridge connecting 2 substrates, and the bridge is half merged in the electrolyte. So in these systems, we have 2 dominant forces. The first is capillary pressure, which is the function of surface tension of liquid metal, and also the liquid metal interfacial tension, also contribute to the overall capillary force. In fact, the interfacial tension force always trying to pull these two substrates towards each other. So that's the reason why it has a negative sign. So by controlling the interfacial tension, we found that we are able to induce contraction and extension of the liquid metal bridge, thereby making like a kind of liquid-based artificial muscle. I think it's better to use the footage to show the concept, but instead of using one droplet here, we use numerous, like 4 droplets to drive some loads. As you can see, this is a real-time video. The response time is okay. It's around like milliseconds. And it can be actuated in different solution. Although in solid chloride or chloride solution, the stroke is a little bit less. Also in acid solution like hydrochloric acid, the response time is also fast and the stroke is good. So using these kind of liquid metal artificial muscle, we use it to drive the caudal fin of a bionic fish. So I think this footage shows the story. Simply using 2 droplets, we're able to actuate the caudal fin at different frequencies, but we found that at 2 Hertz, it actually gives the best propelling efficiency. As you can see, this footage shows the top view and front view or the side view of the actuation of the bionic fish. Because unfortunately we made the fin transparent, so it's a little bit difficult to see from the side and from the front view. But I believe you can see the actuation of caudal fish from top view. Finally, I'll briefly talk about liquid metal droplets. Using liquid metal droplets as robot and themselves as robotic systems. So in this case, we created arrays of electrodes which are controlled by phototransistors, and the surroundings we made a circular shaped graphite electrode, and upon activating individual phototransistors, we're able to activate the corresponding electrode, thereby attracting the droplet towards the activated electrode, and the active electrodes are acting as anode. So this footage shows that the droplet is able to follow the position of the laser spot. Here we used red light to show it. Actually, in the real experiment, we use infrared, so we're not gonna interfere with the vision. Using this method, we actually created we call it liquid metal cat, because cats are always obsessed with laser light. So I'll just quickly show the video. I think I'm running out of time. We're able to control multiple droplets using multiple beams of lasers. And we can control the coalescence of liquid metal droplets, splitting of liquid metal droplets using these methods. Yes, and finally, I'll just quickly talk about recent work on the instead of control the locomotion of the droplets, we also are able to control the morphology of liquid metals. In this case, we mix liquid metal with some iron microparticles to create a liquid metal iron particle share on the surface, and the share is able to engulf pure liquid metals. And by doing this, instead of actuating liquid metal upon application of external potential, we're able to elongate a droplet of liquid metal using a cathode to guide it. And the elongated length is more than 10 times of its origin body length, which is significant. It's quite kind of surprising to us. And this made me think about, I believe watched the movie Terminator 2, like the T-1000 liquid metal robot is able to elongate its finger, the arm to turn into a sharp blade. we're trying to borrow the similar idea, and the principle is relatively simple, straightforward. It's basically just oxidize one side of liquid metal, so it's able to elongate and driven towards the cathode. And we tried different doped with different particles, and it seems like on particles, this higher standard electrical potential works. High standard electrical potential than gallium works. And also the separated core behaves exactly like pure liquid metal, which only going to migrate towards the anode, as we demonstrated previously. And also, like if we inject a little bit more fresh liquid metal inside the shell, the droplet still can be elongated, similar to the freshly prepared mixture. So I think I'll play one more video so to conclude this talk. The biggest advantage of this method is we are able to control the morphology without any channel constraint. We're able to write complex letters with like even very sharp angles. Like we try to write C, like this time we'll try to N with very sharp angle, approximately 30 degrees. And I'll just make it faster. And yeah, we can also write the letter Z. So all of this can be guided simply with copper electrodes, and without any channel constraint. We can also write even more complex pattern like the letter B. And of course, like many other letters like R and A. So yeah, I think since I'm running out of time, I'll conclude today's talk. So the advantage of liquid metal robots, including the principal operation, is simple. Like we just simply use continuous electrowetting, electrocapillarity, or electrochemistry. And we avoid using conventional rigid mechanical moving parts, and soft. All the actuating components are soft, and because they're soft, no mechanical moving parts, so the noise is low and the maintenance is relatively simple. But I still have to point out that the few things needs to be investigated further. First is how to improve the energy efficiency, and we still have to actuate everything in the electrolyte, how we're going to remove the electrolyte, and how to increase the system complexity is our next step of investigation. And I would like to thank all my collaborators, and students, and funding agent who make all this research possible. Thank you so much for attention.